Welcome back to the series.
Before anyone can meaningfully talk about attackers, vulnerabilities, or controls, we have to answer one foundational question. What are we actually protecting? In security work, this is known as identifying the crown jewels, the assets where loss, manipulation, or exposure would cause outsized harm. This video is critical because quantum vendors often misidentify their most valuable assets. They assume it's source code, chip designs, or published algorithms. In reality, AI for quantum systems, they shift value away from static artifacts and toward dynamic, learned, and operational assets. If you protect the wrong things, you can spend millions on controls and still lose what matters most. Why AI changes what counts as a crown jewel? Traditionally, intellectual property was human-readable, documentable, and relatively static. AI breaks that model. In AI-enabled systems, value concentrates in data, learned representations, and execution context. Quantum systems amplify this effect because devices are highly individualized, performance is fragile, and small advantages they compound dramatically. So this video reframes what valuable means in this domain. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence. High-level categorization of crown jewels. We'll group the crown jewels into two broad classes: technical assets and legal and business assets. Technical assets, things that directly affect system performance, correctness, or competitive advantage. Legal and business assets, on the other hand, things that create regulatory, contractual, or reputational exposure if mishandled. Both matter equally. Losing one often cascades into losing the other. Technical crown jewels. Asset 1. Raw experimental telemetry. Let's start with the most underestimated asset, raw telemetry. This includes readout traces, calibration sweeps, timing data, noise measurements, environmental signals, experiment logs. Why this is a crown jewel? Because telemetry is not just measurements. It is a record of how your system behaves in reality, not in theory. AI systems can extract from telemetry device-specific noise fingerprints, correlations humans don't notice, and latent parameters that define performance limits. From a competitive and security standpoint, this is extremely valuable. If an adversary obtains sufficient telemetry, they may not need your hardware designs at all. Asset 2. Derived device, fingerprints, and models. Closely related but distinct are derived representations, noise models, error models, device embeddings, learned representations of qubit behavior. These often live in trained ML models, configuration files, serialized parameters, or optimization heuristics. Why these are crown jewels? They encode months or years of operational learning. They are far easier to exfiltrate than hardware. They are difficult to reconstruct from publications alone. From a legal standpoint, these often qualify as trade secrets, even if the underlying physics is public. Asset 3. Control parameters and calibration outputs. Control parameters include voltage schedules, pulse shapes, timing offsets, feedback rules, calibration solutions. These may look mundane, but they're extremely sensitive. Why? Small changes can drastically alter performance. They often differ per device. They can reveal internal system structure. In AI-driven calibration systems, these parameters are often generated automatically, updated frequently, and deployed without human review. And that makes them both valuable and vulnerable. Asset 4. Error correction decoders and models. Quantum error correction decoders, especially AI-based ones, are a major crown jewel. They include model architectures, trained weights, inference pipelines, accelerator implementations. Why they matter? They directly affect logical error rates. They can be tuned to specific devices. They are hard to validate externally. A compromised decoder may silently degrade results, bias outcomes, or create subtle availability issues. From a trust perspective, this is one of the highest risk assets in the stack. Asset 5, FPGA and Accelerator Bitstreams. When decoders or control logic that are implemented on FPGAs, GPUs, or other accelerators, the bitstreams and firmware, they all become crown jewels. Why? They are executable logic. They're opaque to most review. They sit below application level security controls. Tampering here is particularly dangerous because it can evade detection, it can persist across updates, and it can undermine correctness guarantees. Quantum compliers and optimizers, they often include mapping heuristics, scheduling strategies, hardware-aware optimizations. Even when the compiler is open source, the configuration and tuning are often proprietary. AI-assisted optimization further concentrates value. The how becomes learned rather than explicit, and behavior may differ subtly across devices. These artifacts, they determine performance, cost, and customer satisfaction. Asset 7, customer circuits and workloads. Finally, never forget your customers' assets, they become your crown jewels. Customer circuits may represent proprietary algorithms, sensitive research, regulated workloads. Even if you don't understand the semantics, you're responsible for confidentiality, integrity, and non-tampering. Any threat model that ignores customer IP is incomplete. Now the next part, legal and business crown jewels. Asset 8, trade secret status itself. Trade secrets only exist if information is secret. It derives value from secrecy, and reasonable steps are taken to protect it. Poor security controls, they can destroy trade secret protection even if no breach occurs. From a legal perspective, failure to protect can equal disclosure, and this makes security controls part of your IP strategy, not just IT hygiene. Asset 9, controlled technical data, export control. Certain quantum-related information may be subject to export controls, deemed export rules, national security regulations. This can include performance characteristics, control techniques, detailed telemetry, or advanced error correction methods. Once classified as controlled improper access, even internally, it can create legal exposure. Asset 10, customer trust and contractual assurances. Many quantum vendors, they operate in government, defense, finance, or regulated research environments. Customers will ask, how do you protect our data? How do you ensure correctness? How do you prevent tampering? Failure here doesn't just risk breach, it also risks loss of market access. Asset 11, regulatory posture and audit evidence. Increasingly, regulators and customers, they expect logs, provenance, access records, model lineage. The ability to prove what happened becomes a crown jewel itself. If you cannot demonstrate control, you may be treated as if you had none. So why crown jewels shift over time? One important nuance, crown jewels are not static. As AI systems evolve, Models may become more valuable than data. Automation may increase the blast radius of errors. Collaborations may expand exposure. And this is why crown jewel identification must be revisited regularly. Common failure modes at this stage. Organizations often fail here by focusing only on code, ignoring data and models, assuming internal assets are low risk, or underestimating legal implications. This video is designed to prevent that failure. Now that we've identified what matters most, the next step is to ask, who might want these assets and why? The next video introduces the threat actors most relevant to quantum vendors and developers and explains their motivations and capabilities. So understanding adversaries is essential before discussing controls. I'm Nupur Mitra, a legal and governance risk translator for AI systems. On the AI law, I unpack how AI security flaws, governance failures, and model behavior, they all turn into real legal exposure, rights issues, and the future of jurisprudence.